Hi, I'm Joel Crabtree, and this is my Lab 1. I modeled a object moving at a constant velocity and observed its position in respect to time. To do this, I created a glowstring model to predict the movement of my object, and I used tracker software to measure the movement of that object. What I did was I rolled a can of soda across the floor in my kitchen, and using tracker and glowstring, with tracker I modeled its movement in respect to time, and with glowstring I predicted the movement of the object. Here's the predictive model. I found the mass of the can online to be 0.368 kilograms. I measured in intervals of 0.167 seconds. I determined the position of the ball and updated it using the position update formula without accounting for acceleration, assuming it will be zero due to Newton's second law, which states that net force is equal to mass times acceleration, which would cause the which would necessitate the acceleration to be zero. Here is the model. As you can see here, velocity remained constant and position increased consistently. Here's the data. Here's my live experiment. Using tracker, I plotted it on this axis and have measured the position in each interval. So you can see here, in those intervals of 0.167 seconds, I've measured it, and here I will plot this data in respect to the predictive model and see how well they align. Here is the predictive model data versus the live experiment data. The predictive model data is modeled in red dots, and the live experiment data is modeled in black dots. As you can see, they nearly overlap completely. This shows a high correspondence between the model and the experiment. There are some ways, though, that could account for the discrepancies and why the model did not perfectly predict the movement of the can in the live experiment. I'll go over that now. The main idea in this experiment is Newton's second law, which allows you to derive the net force of the object, and assuming that the acceleration will be zero, as it would be if there was constant velocity, there would be net force acting on the can, and the can will travel at a constant velocity along the x-axis. The discrepancy between the predictive model and the live experiment can be explained by there not being exactly zero acceleration in the can while it was moving when I rolled it, though it seems there was very little, as the position lined up very similar and very near to the predictive location. There may have been a non-constant acceleration, and there may have been some level of acceleration causing the discrepancy there. One question raised is if the positive x and negative x-axis were flipped in tracker, how would this affect the position? If that had happened, the magnitude of the position vector would have remained the same, while the position would have, all the position values would have been in the negative x direction rather than the positive x direction. If the forces added together all equaled zero, then there would be zero net force acting on the object. This may not have happened. What should have happened was the friction of the surface and the air resistance acting on the can would have canceled out the force. It would cancel out the force in the positive x direction when I rolled it. There may have been an imbalance there, causing there to be some net force acting on the can, and there was also forces acting in the there was also gravitational force acting in the negative y direction on the can, and the normal surface force of the can acting in the positive y direction. I assume that would have been zero net force acting on the object, and I think it's more likely that my rolling of the can there was some exertion of force where the force did not even out with the force of the friction of the surface and the air resistance. So to conclude the experiment, it seems that the position of an object traveling at a constant velocity can be very nearly predicted over a short distance and with a small object, though there are discrepancies in the data which may be due to the inability to neatly roll an object with zero acceleration. I think that is the most likely explanation for why the predictive model did not exactly line up with the experiment. That concludes my presentation. Thank you.